qui à Florian Biermann und Dr. Martin Science.
So good afternoon. I will not use a microphone because I have a very loud voice. And it is very nice that Ross gave this talk before because he mentioned the deferred acceptance algorithm. And this algorithm will also play a role in this paper, which is co-authored with some people from Southampton University, from the Department of Computer Science. And in this paper, the deferred acceptance algorithm will be, if you want, an approximation of what we think how people behave. So while usually it's an algorithm which prescribes the behavior and which is used to construct a matching, here we think that it describes the actual behavior of the agents. So what we're doing is an extension of the standard assignment problem. And we believe that in many situations, in many real-life situations, the central planner who assigns workers to tasks cannot absolutely surely determine what these workers are doing. We think that in many situations, workers have certain discretion what they're really doing. And so we are looking at a situation where there are agents which are totally controlled by the central planner, and there's another group of agents whose members are doing what they want to do themselves. So the question is, how can the central planner find an overall optimal matching, given that some of the agents are not directly controlled by him? So let's quickly review the standard assignment problem. We have a set of agents, and we have a set T of tasks, and an assignment or matching is a subset of the Cartesian product of A times T, such that if there are two pairs in a matching, then both components of these pairs must be different. Okay, so not two pairs can share a member. Then there is a function v which assigns a value to each pair, and the goal of the central planner is to maximize this expression, which is the sum of the value of all pairs which are in the matching. To find a matching which has an optimal value. And this can be done, for example, with a Hungarian algorithm of Kuhn 1955. Well, let's look at a practical situation. What if not all agents obey the central planner's commands? Here we have Eyal running the Center for Rationality in a situation where three of his resources are idle. I am idle, I'm his PhD student. Here I have shorter hair because I just have long hair since some months. And the other resource is Sergio, who also is asking Eyal what to do. And the third resource is Romina. So Eyal applies the Hungarian algorithm. And after he has done some calculations, he comes up with the following solution. Florian, please work on your PhD. And he tells Sergio to work on game theory. And finally, he tells Romina to prepare a conference. And what happens then? Okay, all three resources go to their desks. But and Eyal doesn't keep control. Eyal now starts working on his own stuff, so he reads in the Games and Economic Behavior journal. What am I doing? Okay, first thing I do, I jump over my desk and hide behind it so that nobody can see me. And what am I in fact working on? I'm working on forensic pathology. So this paper I wrote during my PhD, which is not connected in any way to my PhD. Even worse, I'm playing chess. So you can see me playing chess here. It was outside here in Givatram, and we had a funny situation where there were real people who were copying this board, and they had to, when I moved one of my pieces, and someone had to move on this large board. And I was indeed playing a lot of chess when I was here in Jerusalem. What is Sergio doing? So Sergio pretends to work on game theory, but in fact he works on convergence properties of sequences of random manifolds in infinite dimensional Banach spaces. So in fact he's working on a problem of pure mathematics. So also Sergio is not doing that. Well, right.
That's something misrepresentation.
So you see, also Sergio is not doing what he was supposed to do. The only one who is really doing what she was supposed to do is Romina. That's why we are here, because she was supposed to organize a conference. Sergio, Eyal is desperate. What did I do wrong? Nobody does what he calculated to be the optimal solution for the center of rationality as a whole. Some agents pursue their own interests, their own agendas. And that's the topic of this paper. We solve assignment problems in which some of the agents follow their own agendas. We give some more serious examples, because I think the examples are the most important part of this paper, because I think it's really a very relevant question. Military campaigns in which rebels ally with regular armies. Take the Libya campaign we had this year. There was the NATO, which deployed these kind of units. Like professional soldiers, they could be deployed anywhere in Libya, and they did what they were told to do. But they were cooperating with these people, with rebels who had some properties we talk about. They, for example, do not have a chain of command which connects all of the units with the central command. Okay? They have units which are led by competing local leaders sometimes. This makes it even worse. They might have competition among these units. They are highly decentralized. And they lack discipline. I mean, look at them. As soon as they have burned a car, they're having a party. So this is, of course, this is something totally different than a NATO pilot. Nevertheless, the rebel forces may be crucial for the campaign success.
That's the same concept when he gets back to bases. That's
Sorry?
not a difference. He has the party when he gets back to the bases.
Well, but
After burning the car.
from an efficiency point of view, it makes a difference, I guess. Well, the rebel forces are extremely important, because in many wars we had in the last 15 years, they were the only ground forces. Think about Kosovo. Think about Afghanistan. There was this Northern Alliance, which was supported by NATO. And think about Libya. Usually the Western countries don't want to engage on the ground, because there are too many casualties. So they leave the groundwork to some locals, and they're just supporting one side with planes. And so they are extremely important, these rebels. But from the point of view of the NATO, this is a semi-autonomous assignment problem. This is how we call it. And an assignment problem where some of the agents do what you tell them, your own forces, but others don't. Others have their own agendas. Similar problem, disaster response. We have, after an earthquake, for example, we have professional rescue forces. Again, they do what they're told to do, and they even have equipment like helicopters, so they can be deployed anywhere in the relevant area. On the other hand, we have survivors. So for example, here is a family which is digging for maybe people who somehow got covered by debris or something. And these people are not irrelevant. Why? It's true, they are not coordinated by a central command. But they are led by local considerations. For example, a very straightforward heuristic, how they could select the sites they are approaching, could be the distance. So after the survivors have found out that they're still alive, they go to the emergency task which is closest to them. And on the other hand, they potentially lack discipline. For example, there might be still another earthquake or something, and it might let them to flee. And they're not staying where they are. So nevertheless, they are extremely important because they are close to the critical sites. They have strong incentives to help, usually, because it may be their relatives who are somewhere buried there. And they are well acquainted with the local conditions. Again, from the point of the central disaster response, this is, again, a semi-autonomous assignment problem. Finally, very quickly, because I don't want to... So I'm talking until 10 minutes to 4, right?
Yeah.
Oh. Yeah. Okay, that's correct. Okay. Okay, so I started 20 past. Okay. Well, an army with ambitious officers. And take this guy. He's called Tordenskjold. He lived from 1691 to 1720, and Tordenskjold means Thunder's shield. He was a naval commander of the Danish fleet in the Great Northern War at the end of the 18th century, the beginning of the 18th century. He notoriously disobeyed orders. For example, in the Battle of Dunekillen, 1716, he had just 7 ships available. And the Swedes, they not even assumed him to attack. But he attacked, and with his 7 ships, he captured 31 Swedish ships, and he destroyed another 13. So it was an extremely successful commander. What were his incentives? Well, he had great prestige gains. He appears in 2 national anthems, in his homeland Norway and in the national anthem of Denmark. And finally he became an admiral, though he was sued at a court martial before, because he always disobeyed the orders. He never did what they were told, what they told him to do. And from the point of the admiralty, I mean, if you have such a guy in your army, it's a semi-autonomous assignment problem. Because some people, they really do what you tell them and others don't. Okay. Formally, we have now, in the semi-autonomous assignment problem, we have a set of agents which can be subdivided into C and F. C are the controlled agents, and F are the free agents. The intersection is empty. Each free agent F has a linear order defined over a subset of the tasks. So this could be interpreted, for example, in the disaster response scenario, as those tasks which are not too far away. If they're too far away, then there's no chance that this free agent will approach a task, so they are those which are accessible. Due to the antisymmetry, a linear order does not allow for indifferences between unequal elements. That makes things easier, it makes the analysis much easier. The free agents approach the tasks in tau F, the free agent F, sorry. The free agent F approaches the task in TF according to the order, I call it weak F. Okay? So he goes first to the most preferred one, then the second, and so on. Given he doesn't take the first one. So we will see how it pans out. How can this be interpreted? Yes, I told it already. This may be F, and the red points are possible tasks.
Disjoint, right? Each one has only one person doing the task, right?
No. There could be these sets, tau F for 2 different F, could be overlapping. There could be overlapping, that's important. Well, I mean, let's assume we are both survivors, and we are standing next to one house. It could be that either you go into the house and check for people.
It's not an assigning problem, one-to-one. We're talking now about personals.
Well, I mean, it's similar. Also, in the standard assignment problem, it could be that 2 workers are eligible for the same task.
No, I'm asking not a feasible set. I'm asking about the final assignment.
No.
One-to-one.
You're right. It's one-to-one. It's a matching. It's a matching. Yes. Okay. So these are now. This is a feasible set, and he first goes to T1 because he had these preferences: T1 preferred over T2, preferred over T3. Now we will explain why does he not take T1. We will explain that now. Then he goes to T2, and if he doesn't take T2, then he goes to T3. Okay, and T4 and T5 are not in his feasible set, so he will never approach these tasks. How does this process of tasks of decentralized task assignment, how does it proceed? Now these are all the tasks, and these are the free agents. Now we assume that first of all, the central planner assigns his agents. So now some become green. These are those which are occupied by controlled agents. Okay, and we will release this assumption. We'll see that this is not a strict assumption that the central planner moves first. Then we let the free agents approach those tasks which are best according to their preference orders. And if we have a task which is not competed, like this one for example, then just this free agent gets a task. Otherwise, if we have competition, like for example, here's 3 free agents are interested in the same task, we assume that only that player gets a task which has the highest contribution, the highest value for the task. Okay, so here, for example, it was this player, and this guy took another task, and also this guy took another task. Here again we have a situation that two players are competing for the same task, and again, one of them moves away. The one which has the lower contribution. Yeah?
Sorry, are you describing now a problem or a solution of the problem?
No, this is a problem. This is our assumption on the behavior of the free agents.
An algorithm.
Yes, it's right. It's,
what problem?
this is not an algorithm. This is I said at the beginning when you weren't here, the deferred acceptance algorithm in Ross talks is something which prescribes behavior or which is used to construct a certain matching. Here, we think it describes behavior. This is how we think how the free agents are moving.
Your primitive is a procedure.
Yes, it's a primitive. It's a primitive, exactly. It's a primitive.
Okay, go on.
So, as you have already found out, what the free agents are doing is in fact they apply the deferred acceptance algorithm. Okay, in this marriage market, T, V, F, and the weak preferences. TV are those tasks which are not occupied by control agents. We said that they were already out of the game when they turned green. F are the free agents, and the preference profile of the free agent is the one which we already described, and the preference profile of the tasks, the preference of the tasks are determined by their value, by their performance. So if a task has to decide between, of course it is fictitious, I mean tasks in reality don't have preferences, but it's a way how to deal with this problem. So if a task prefers one free agent over another, then this means that this first free agent has a higher value at that task. Okay? And then if we run the deferred acceptance algorithm, we exactly get this behavior which we just described.
So in the picture that you showed, once an agent is the only agent, it appeared as though it's over. But it's not what you're saying here, because maybe later some other agent will compete.
Right. I pointed at one in the graphic where indeed nobody approached that task. Right. But you're right, in principle it could. I mean, if it goes on for some more time, but in this particular instance which I presented, it
didn't happen. But
it didn't happen.
It could
happen, yeah, it could happen, right. So we ensure linearity of these orders by saying that whenever there are two different pairs, then the value is also different. Okay, that's an assumption, so that also the linear preference order of the tasks are linear. Okay, by McVitie and Wilson. Now this is very robust in my opinion, this way to model it. By McVitie and Wilson we know that the fact that the central planner assigns his control agents first does not change the final outcome. As long as the central planner always has priority, as long as the central planner can always take away tasks which were already occupied by free agents. Furthermore, the order in which free agents move is irrelevant. So whether we let all of the free agents move simultaneously or we have some sequence, it doesn't matter.
Wait, I'm sorry. The central planner knows the preferences of the free agents.
Yes, we assume that.
And takes them into account when he computes it.
Yes? Right.
Okay, that's a big assumption.
That's a big assumption, absolutely.
And you think Admiralty knew the preferences of this guy who never listens to what Admiralty says?
Well, I mean...
Saying that, or that NATO knows what the rebels are doing. That's exactly
well, I mean, I don't think I agree with you that
NATO can take into account exactly what those uncontrollable agents are doing. Is, in some sense,
well, I agree with you that it's a strong assumption, but it depends on the application. For example, in the disaster response... but I want to say something about it. I mean, in the disaster response application, the assumption that people choose tasks according to distance is not too far-fetched, in my opinion. I mean, what other criteria should people have? Well, I mean, of course.
Knowing who the free agents are, knowing what's going on there, that's a very big assumption.
I can give an example when you are right.
Okay.
The Afghani war, which I researched, the Afghani army, the Afghani National Army, and the Afghani National Police behave like free agents, but because they have an American and a NATO officer at each unit, they know what those free agents are doing.
Well, you see.
So it's a case which is between
Definitely. The same thing it works.
By the way, the same thing happened in Iraq.
The same thing happened in Iraq.
So you have to.
Well,
We cannot give up.
There are two types of balagan in this world. Okay, it's
well, that's okay. I mean,
I just understand the assumption because it was not clear before. So
okay. We want to formulate a problem, the problem as a mathematical program. That's the goal of the paper. That's what we're doing in the paper. So we want to have something which we can solve with a computer. And how we do it, the idea is, our way how to do it is that Nash equilibria of zero-sum games, like the one in Neumann in 1928, can be represented as solution of mathematical programs relatively easily. So what we have to find a zero-sum game whose Nash equilibria coincide with optimal assignments of this semi-autonomous assignment problem. Do we have such a game? Yes, we do have it, and we call it disjunctively constrained knapsack game. How does it work? The central planner and an adversary, AD, play a game, and the CP moves first, the AD moves second, so it's a Stackelberg game. The central planner and the adversary jointly fill a knapsack, K, with elements from the Cartesian product of A and T. The value of the knapsack is defined as the value of the elements which are inside, but the central planner wants to maximize this value. 5 minutes, oh great, okay, that's cool. And the adversary wants to minimize it. So therefore it's a zero-sum game, okay? The central planner has the action set to choose any matching under which no free agent is assigned. On the other hand, the adversary action set is to find a stable matching in the marriage market which occurs after the central planner has already assigned its agents. So we have like a little bit clumsy notation here, just say that this stands for the marriage market which we have after the central planner has assigned its players. Well, the actions which are chosen, okay, we let ACP and AAD be the actions which are chosen in one play of this game, then this is an element of, this is a matching, the outcome is a matching, okay? Must be the case because in one part of the pairs you have always a free agent, and in the other set of pairs you have no free agents. Therefore it cannot be that one player is in two pairs here, okay? And furthermore, it has a unique Nash equilibrium if we have that no two matching has the same value. This follows from the fact that under any zero-sum game, all equilibria have the same payoff vectors. Okay, so it's pretty direct. Okay, the theorem. So let ACP and AD be the actions of the central planner and the adversary in this game. Then, if their choice is a Nash equilibrium, then this outcome is an optimal solution of the semi-autonomous assignment problem.
Can I ask a question?
Yeah?
It appears that we're looking for the worst possible response that the free agents can offer, and not necessarily taking it as given and trying to maximize the likelihood of my control agents.
Again, I don't...
There are two different problems you're going to look at. One that you're looking at seems to be where I have the control agents, and the free agents are going to try to find the worst possible allocation for me.
Yes, which is a stable matching.
Another possibility would be looking at the free agents' preferences as given, and then finding the best way to use my control agents.
Well, I mean, but that's what we're doing. I mean, the fact that they try to get the worst outcome after the central planner has moved, it has a reason. It has a reason. It's because then it will be the same outcome as the outcome of the deferred acceptance algorithm. Because the deferred acceptance algorithm with free agents proposing provides the worst stable matching for the tasks. You see, therefore it's the same. I can give the proof of the theorem, or at least the sketch. The deferred acceptance algorithm, I'm done in 2 minutes, okay? The deferred acceptance algorithm in this market, with free agent proposing, constructs the worst stable matching, μF, for the tasks. But in the way we constructed the preferences, this means that any other stable matching in this market must have a higher value. Okay? And therefore, if the second player, the adversary, tries to minimize the value, it must be the same matching as the one chosen by the deferred acceptance algorithm. So there is a coincidence, you see? And in equilibrium, we can now write the choice of the adversary as a function of the choice of the central planner. Because whatever the central planner does, the adversary always tries to minimize the matching, the stable matching in the remaining market. And therefore, the central planner chooses that action which maximizes this value, which is then, of course, the optimal solution of the SAAP, and it's a Nash equilibrium. And finally, we can use this fact that it is a zero-sum game to write the optimal solution as a max-min problem with these two constraints. Okay? This is not easy to be solved. It's a bi-level mathematical program. It's difficult to be solved, but at least we have a way how we can find the solution with a computer. At least for small problems we can solve it, and there's a huge literature on how to solve these problems.
Is it exponential in the science?
Sorry?
Is it, what's the solution? Is linear, exponential?
It's not a linear program. It's not a linear program. Neither in the.
Is it NP? Do you know if it's P?
Well, I don't know exactly. But it's very difficult. We asked somebody who is expert on these, and he said it's very hard. It's very hard to solve this. Okay.
The claim that the stable pairing is the worst for the tasks assumes that tasks are set. TV here is not set. The planner has to choose what TV is. Given TV, this gives us the worst possible.
Yes, it's a two-stage game. It's like a Stackelberg game. First, the CP moves, and the AD takes as given what the CP has taken. So you could say the strategies of the AD map any choice of the AD of the CP into an answer, into a reply of the CP. You see? So therefore, I mean, in the original version of 1928, it's not a Stackelberg game. It's a simultaneous game. It's a one-shot game. But this corresponds to a one-shot game in a direct way.
We have here, I mean, zero-sum game. We have here convexity. Are those assignments or something convex? I mean, the strategies to have max min equals min max or something. We need new strategies. Should we convexify the set or something? Or do you know that that's always happens in new strategies?
Well, I mean, I took it directly from 1928. And you can directly, I mean, for Neumann Morgenstern, you can directly take his abstract form with actions and so on, and
so a set of new strategies. It's not pure strategies. Your assignment, set of assignments corresponds, I think, if I understand correctly, pure.
So you say it doesn't hold for pure strategies? Not necessarily, you say.
You may not find a solution in pure strategies. What if he computes these and he comes up with a mixed strategies?
Well, I mean, we have these restrictions that it must be. Doesn't this solve the problem? Well, it's an interesting problem. I have to check that. Sorry, I have to check that. Okay. Okay. Thank you very much.
We are behind our